Hi everyone, in this video we're going to go over section 5.6 on defining sequence recursively. So what are recursive sequences? So a recursive sequence or recurrent relation is a sequence in which terms are defined using or more of the previous terms which are given by our formula. So the components of a recursive definitions are the initial condition is given, so we have some starting values that are given explicitly. Number two, we have a recurrence relationship, so a formula that is expressing each of the terms using previous terms. The general form is going to be something like this. So the initial is going to be your term A0 is this number C0. Your term A1 is this number C1. Those are called the base cases. And then you have the recurrence, which is the AN is a function of the previous one, like AN minus 1, AN minus 2, for any n bigger or equal than k. Now, the key difference here with an explicit formula is that when we have an AN equals f of n, you can compute any term directly. For example, we have a of n equals 2n plus 1. And if we want to compute a of 100, we just plug 100 and immediately we're just going to get 2 times 100 plus 1, 201. In a recursive formula, though, we must compute the previous terms first. So for example, we have the A0 is equals 1 and AN is AN minus 1 plus 2. So as you can see, it's not very easy to find what is 100. To find 100, we need to find A99, A98, A0, A1, A2, all those values. Let's see some examples of that. So suppose A0, A1, A2 are defined as follows. We have A0 is 1 and E1 is 3. Now the recurrence relationship is EK is 5 times EK minus 1 minus 6 times A of K minus 2 for K bigger than 2. We want to find out E2, E3, and E4. So notice that we start by using the recurrence relationship. So to calculate A2, notice that that's going to be 5 times E1. If we plug 2 here, it becomes E1. And if I plug 2 here, it becomes E0. So we have 5E1 minus 6E0. Because I have those initial values and I can actually compute it. 5 times 3 minus 6 times 1. This is 15 minus 6. This is going to be 9. Now, same thing happens if I want to calculate E3. Now, E3 will be 5 times E2 minus 6 times E1. So it's always in terms of the previous two. Because now we have E1 and E2, then we can just calculate that. It's 5 times 9 minus 6 times 3. And it's going to be 45 minus 18, 27. Now, if I'm going to do A4, then I need to compute 5E3 minus 6E2. Notice that I had to compute first E2 and E3 in order to be able to do E4. So in this case, now this is 5 times 27 minus 6 times 9, and that's going to give me 81. So the entire sequence is going to be 1, 3, 9, 27, 81. These are powers of 3. Actually, I can find a formula for en in this case. E to the n, or E of n, is going to be 3 to the n. As you can see, 3 to the 0, 1, 3 to the 1, 3, 3 squared, 9, 3 to the 3, 27, 3 to the 4, 81. So we do have a pattern here, and we can find a explicit formula. Can I always find explicit formulas for sequences? Not necessarily. So there are some sequences that are going to be recurrent, and I'm not going to be able to find a pattern. But for some of them, like in this case, it's possible. Now let's introduce one of those sequences that I'm not going to be able to get you n-term formula, which is the Fibonacci sequence. So the Fibonacci sequence is often referred as the sequence that is given by f of 0 equals 1, f of 1 equals 1, and the recurrence f of k equals f of k minus 1 plus f of k minus 2. So pretty much the next term is always going to be the sum of the two previous. And we start at 1. So if I want to get the first terms, so like f of 0, 1, f of 1, 1, those are given. F of 2 is just the sum of the previous two, so 1 plus 1 is 2. F of 3 is the sum of f of 2 plus f of 1, so 2 plus 1 is 3. F of 4 is f of 3 plus f of 2, so 3 plus 2, which is 5. And f of 5 is f of 4 plus f of 3, which is 5 plus 3, which is 8. Notice that this is like 1, 1, 2, 3, 5, 8. Then we can go to 13, 21, 34, 55. So there's not an easy pattern that you can get in here. Now, a Fibonacci sequence appears in nature. Spiral patterns in nature, like sunflowers, pine cones, and Nautilus shells, they actually have the measure of Fibonacci on how the areas are distributed in some of the patterns. This also shows like in branches trees, in arrangement of leaves, and rabbit population growth, which was the original problem that got the Fibonacci sequence, in the golden ratio, which is where actually the ratio between the n plus 1 and the n term converges. You take the limit when n goes to infinity of that ratio, you're going to get what is called the golden ratio, which is the number 1 plus the square root of 5 over 2, which is like 1.618 more or less. This was named after Leonardo Fibonacci. And in particular, the golden ratio is something that you're going to see that appears a lot architecture in nature. Another recurring sequence that is going to be meaningful is the one given by the Tower of Hanoi, which is a game. It's a puzzle game that you might have seen. The puzzle is that you have a bunch of discs and you have 3 poles. And so the idea is that you want to decrease the size pile on one pole and move it to another pole. So you want to do something like moving all the discs from the pole A to the pole C, and you can only move one disc at a time, and you can never place a larger disc on top of a smaller disc. So that's the challenging here. So the key question here is how many moves are required to transfer n disk. Here, the more disks that you have, the more complex the answer will be. So we have a sequence that we're going to call m of n, and it's going to be the minimum number of moves to transfer n disk. So this is going to be a recursive movement because notice what we need to do. To move the top N1 disk from A to V using C as an auxiliary is going to require n of n minus 1 moves. First, you move the bottom disk from A to C, and that's going to require one disk, so that you're going to move this one, and you move it to C. Okay. And then you move n minus 1 disk from B to C using A as an auxiliary. So notice that you first move all this disk using C to get to V. And then once that you get to that point, then you gotta move it back. Now, to move n minus 1 disks from B to C using A as an auxiliary, it requires n minus 1 moves. So that's the position after transferring k minus 1 disks from B to C. So we do the whole transfer from here to here and then finally to here, but we got to move all the others. So because it requires all those moves, then the total sequence is going to be given by the recursion m of n equals m of n minus 1 plus 1. And plus m of m minus 1, which will be the final step. So that means that the recursion is going to be twice m of m minus 1 plus 1. And remember, once again, this is the number of movements that requires to move that number of disks. So the recursive definition of the Tower of Hanoi is going to be the initial is m of 1 equals 1. And the recurrence relation is going to be m of n is in terms of m of n minus 1 by 2m of n minus 1 plus 1 for any n bigger than 2. So we can compute some values here. So for example, if m of 1 is 1, then m of 2 is going to be 2m of 1 plus 1. So it's going to give me 3. Then I can compute m of 3, the number of movement for 3, this, which is going to be 2m of 2 plus 1. And so that'll be 2 times 3 plus 1, which will be 7, so on and so forth. And so for example, for this disk, it's going to grow very fast. Now we're at 63 movements. So the pattern is 1, 3, 7, 15, 31, 63. All of them are 1 less than powers of 2. So notice that 2, 4, 8, 16, 32, 64. So we can kind of see this explicit formula as 2 to the n minus 1. Now we can verify that that formula is true by induction. M of 1 is just 2 to the 1 minus 1, so it holds. And the inductive step is if m of k is 2 to the k minus 1, then notice that the m of k plus 1 is twice mk plus 1. But then if you replace what m of k is, you get twice 2 to the k minus 1 plus 1, and then multiplying, you get 2 to the k plus 1 minus 2 plus 1, or 2 to the k plus 1 minus 1. So this actually proves that this is indeed the formula for the end step of the Hanoi sequence. Now, notice that when we have 7 disks already, it went already to 127 moves. So this is going really fast. An ancient legend says that monks in a temple were trying to move 64 gold discs according to this rule. And when they finish, the war will end. The reason for that is because if they're doing 1 move per second, the m of 64, so to move 64 discs, will be 2 to the 64 minus 1, which will be 1.8 for 10 to the 19 moves, which is approximately around 5.8 by 10 to the 11 years. So this is around like 42 times the age of the universe. So now let's discuss when to use recursion. In general, we have 2 cases. We have for sequences, we have a explicit formula. And you have things of the form an equals f of n. This is good because we can compute any term directly. And for example, we have the things of an equals 2n plus 1. It's going to be much more easier to compute a specific term. It is better for random access. But the recursive formulas, they need to compute previous terms first. And there's more natural for certain sequences. So this is better for sequential computation. So this pretty much has the structure of a function, and this has the structure of a recursion or a loop. So when you're programming, this makes sense to use for a specific outputs when an input should immediately produce an output. But recursive type formulas, they become more natural when you're using loop programming, and things are in terms of the previous iteration of the loop. Now, you should use recursive definition when each term is naturally dependent on previous terms. The pattern is easier to describe recursively. So for example, for Tower of Hanoi, solve for n minus 1, move 1, solve for n minus 1 again. It could be easier to describe that way. The modeling process that build on previous states is useful. So for example, things like population growth or compound interest. An explicit formula is difficult or unknown. So, for example, Fibonacci has a complex explicit formula. So instead of that, you use the recursion because it's much more easier to explain. Now, this has a connection to induction because recursive definition and inductions are complementary. Recursion defines, and then the induction is going to prove that your recursion is true. They both build from base cases using rules. Now, in summary, you have a recursive sequences are terms that are defined using previous terms. You need initial conditions and a recurrence relationship. We have some examples of that on the Fibonacci sequence, the Tower Hanoi, and we explore the difference between explicit and recursive sequences. It has a very clear connection to induction where they're complementary, and if you define something by recursion, induction is going to prove that it's true. You want to avoid mistake here of forgetting initial conditions. A recursion is never going to be complete without the case basis. You don't want to be using undefined terms. So for example, to compute here A5 equals 2A4 plus A3, you need A4 and A3. You need to complete and compute sequentially using those first terms. You want to be careful with off by one errors. So for example, if we have AK equals AK minus 1, AK minus 2 for K bigger than 2, this requires that K is bigger than 2 in particular. Because notice that when you plug the initial number, 2 is going to give you 0. If this is K bigger or equals than 1, then this one is not going to work because it's going to give you a negative index. So you don't want to have negative index on this. Now, you also want to make sure that you have the right amount of initial conditions. If you have that your AN term depends of AN minus 1 and AN minus 2, then you need 2 initial cases, not just one. So, and you might extend this idea. If your AN depends of the 3 previous cases, then you need 3 initial conditions. Also, be careful with arithmetic errors because one error is going to propagate through the next subsequent terms. So you got to be very careful with your calculations. Okay, this is the end of chapter 5 on sequences and induction. Then we're going to go next to chapter 6 on sets.